All right, silly people, here's the situation. We are going to prove that the Thomas Reich-Kuhn sum rule um, works, where it's this combination of energy eigenvalues and matrix elements is equal to h bar squared over 2m. Um, and the way that we're going to do this is, first of all, we are going to change the energy eigenvalues into a form that looks like the expectation value of the Hamiltonian for these states. Um, and then we'll still have these couple of matrix elements out here like that. Um, and we're going to distribute the expectation values of the Hamiltonian throughout this multiplied like matrix element thing. And we're going to do it in a very clever way. Um, and since these are just numbers, you can move them pretty much anywhere within um, this combination of matrix elements. So we're going to have I'm going to have the n prime h thing go in between the x matrix elements actually. So that's n prime, that's n prime, it's h, n prime, a, x, n. And then the other one, I'm just going to have it stack on top of the rest of the junk because that will suit our purposes just fine. Actually, that's the only way it suits our purposes, but yeah. Um, right. Um, Now, I'm going to make a bold claim that any of these combinations of n prime with n prime or the outer product of n with n uh, just give 1. Specifically, the sum over n prime of the outer product of n prime with n prime is just 1. But this is just the identity operator. And since everything in here is operators anyway, we'll just treat that and let that go to 1 as well. So we'll have just a n x h x n minus n h x x n, which we can combine into one expectation value like that. And what that looks like to me personally is minus uh, the expectation value of the commutator of h with x times left multiplied by x, which also looks like to me minus a half times the commutator of h with x with x. Um, and that's an important thing to have because our Hamiltonian is given by p squared over 2m plus v of x, regular old Hamiltonian. So putting that in there, we have 1 over 2, and then n commutator, p squared over 2m plus v of x with x with x. And but because v of x is going to commute with x, we're just going to go ahead and factor out a 1 over 2m, and instead just look at the commutator of the commutator of p squared with x with x. So simplifying the prefactor a bit by minus 1 over 4m, We can expand the commutator of the commutator uh, as being like p times the commutator p with x plus p times the commutator p with x, and actually the second one would be right multiplied, so it's going to be p with x, p uh, with x, n, right? That's just a commutator rule. Um, both of those commutators do come out to be just minus IH bar though. So we have minus IH bar P plus another minus IH bar P, which we are taking the commutator of with X. And then we can factor out a factor of 2 IH bar. So we'll have 2 IH bar, so it'll just be IH bar over 4M there. And it's the expectation value of the commutator of P with X, which is also just minus IH bar. So we'll factor out an additional IH bar, so it's just going to be H bar squared. And I forgot to factor out a 2 here, but that's where that shows up. You get H bar squared over 2M, and then it's just the overlap of n with n, which is 1. So it's H bar squared over 2M. We did it. We did the Thomas Reich-Kuhn sum rule. The next thing that Shankar asks us to do is to test it on the harmonic oscillator. And there are a number of ways to do this. I've tried one way, and then it didn't work. And I tried this new way, which is a lot simpler, and I kind of like it. So for the harmonic oscillator, we know that the energy eigenvalues are just given by h bar omega n plus a half. And we also know that, and I'm not even going to write it like this, instead of writing it the complex conjugate so formally, I'm just going to write the square modulus, whoops, of n prime x with n squared, and we're going to use a substitution for the position operator for the harmonic oscillator, where it's h bar over 2m omega times the sum of the raising and lowering operators. Okay, so we got that going for us. We can sum over n prime. We'll have h bar omega n prime plus a half plus, or actually minus now, h bar omega n plus a half. And it's going to be multiplied by this squared. So I'm going to have a factor of h bar over 2m omega first of all. And it's the square modulus of that multiplied by n prime a plus a dagger n. Okay. We'll get a little bit of cancellation. This 1/2 will factor out this 1/2, so we'll just have a h bar omega n prime minus n. We can pull out the h over 2m omega just by squaring it. And then the matrix element is now looking like n prime, and then we'll have a raising operator and a lowering operator, so we'll have a root n plus 1 times the overlap of n prime with n plus 1. And then also a lowering operator, so we'll have n, or root n, times the overlap of n prime with n minus 1. And we're squaring that. We can simplify the factors out front. We'll get an h bar squared over 2m. This is already looking familiar. And then in the sum, it's going to be the n prime minus 1. And we're going to square the square modulus now. We'll have a factor of n plus 1 times delta n prime with n plus 1 plus n Kronecker delta n prime n minus 1. And no cross terms because the Kronecker deltas will just kill each other. And so that's what that's looking like. We'll let the Kronecker deltas kill off any of the terms which depend on n prime. So we'll just have we'll have a couple of terms. We'll have one where it's n plus 1 minus n times n plus 1, and another term which is n minus 1 minus n times n, right? And then we'll have a, simplifying these, that is just n plus 1, and this is just minus n. So you get h bar squared over 2m. So Thomas Reich works there too. All right, nice.